So today's lesson is going to be on the electromagnetic spectrum. So what I've got here is a picture of a red and a blue wave, and we're going to kind of introduce a few topics, and then we're going to take this and look at it and apply it to the electromagnetic spectrum. So the wavelength is defined as the length of a wave. And when we look at the electromagnetic spectrum, we're talking about different wave types. So we've got a red wave, and here we have a blue wave. Frequency is how often that wave appears in a given amount of time. So the number of waves in a given time. So let's look at my red and my blue. One up and one down is a wave. So my red has one wave, and in the same time period, my blue has 1, 2, 3, 4, 5. So my blue has 5 waves, my red has 1 wave. So there are more waves in the blue than there are in the red. The wavelength is measured from the point, the top of the wave to the top of the wave. So the top of the wave to the top of the wave, that is our wavelength. And we have this symbol for wavelength. All right, there's our wavelength symbol. And frequency, we're going to use a V for frequency in this particular class. Now, when you get to physics, you'll use an F for frequency, but we do use a V in chemistry. So what do we notice? There's not even a top of the red of a second wave for me to even measure. So the wavelength for the blue is definitely smaller than the wavelength for the red. So we notice that the wavelength for the blue has a smaller wavelength than the red. So I'm going to draw an up. And let's label these both wavelength. Now, what did we notice about the frequency? The red has 1 wave. The blue, we said, had 5. So there's a higher frequency for the blue. And there was only 1, so a lower frequency for the red. So what kind of relationship is this? When we have a larger wavelength and a smaller frequency, when one goes up, the other goes down. That is an inverse relationship. When one goes down, the other goes up. That is an inverse relationship. So wavelength and frequency, that's a V. Let me write that a little bit neater. And frequency have an inverse relationship. What about energy? So waves also have energy. And the way that I like to think about a wave in terms of energy, I like to think about it in terms of if you're at the beach and the waves are just kind of coming in real slow and casual. And so a wave comes in and hits the shore, then another wave comes in and hits the shore. All right, and they just kind of come in versus when there's a hurricane. What happens when there's a hurricane? Those waves come in fast and furious. Boom, 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 boom. One right after the other, right? Wave, 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 bam, bam, hitting that shoreline. Which one is more destructive? When the wave comes in, and then a little bit later there's another wave, or the waves during the hurricane when they're just like coming fast, 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 one right after the other. And in that case, it's a hurricane. Why is that? The hurricane waves have more energy. So these waves have a larger energy. all right, so we have an increase in energy. We have wave coming, wave, 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 versus a wave here, and then another one comes in. So what do we notice about energy and wavelength? Again, energy and wavelength are also a inverse relationship. And what do we notice about frequency and energy? As frequency goes up, so does energy. As frequency goes down, so does energy. So frequency and energy have a direct relationship. Now this is important, and this is going to correspond to our hydrogen Bohr model for an atom. So what we've got here is we have these electrons within our hydrogen Bohr model. So what happens is when an electron is hit with energy, it gets excited. So we have ground state. Let's talk about some vocabulary. And that is where electrons are at the lowest possible energy levels. And then we have the excited state. And the excited state happens when an electron absorbs energy. And it's going to jump to a higher energy level. Now, what goes up must come down. So when the electron jumps up to a higher energy level, it must fall back down to ground state. When the electron falls back to ground state, that is our electromagnetic spectrum. And the radio waves, microwaves, infrared, here's our visible light with the red and blue wavelengths like we just looked at, UV, X-rays, and gamma rays. Now, when an energy or an electron falls to ground state, a light is released in some sort of photon of light, whether it be the radio wave, the microwave, the infrared. So all of these different parts of the electromagnetic spectrum are specifically determined by electron movement. For example, this is ground state, N equals 1, meaning energy level 1. If an electron absorbs energy and jumps up to the second energy level, then it falls back down to the first energy level at ground state. So here's the excited state, and it falls back down. We could follow this, and we see that it produces UV light. If the electron absorbs enough energy to go up to the third energy level, as it falls back to ground state, it emits UV light as well. So looking at this next example, for example, this electron is on the third energy level when in its excited state. When it falls back to ground state, in this case, ground state is energy level 2, it creates a visible light. And so the way the electrons absorb energy, where they move to, and where they fall back to specifically determines what part of the electromagnetic spectrum we are producing. So let's take a look here, and let's try and decide what is happening. And let's look at a radio wave and a gamma ray. Radio waves have a longer wavelength. Gamma rays have a shorter wavelength. So if I'm comparing a radio and a gamma, what can I determine here? The radio wave has a longer wavelength, which means the gamma is a smaller wavelength. We see that, and what do we know? Wavelength is inversely proportional to frequency. So a large wavelength is a small frequency. A small wavelength is a large frequency. And we know that frequency is directly related to energy. So a small frequency is a small energy. A large frequency is a large energy. So gamma rays would have a larger frequency and more energy than a radio wave, and we base that upon our wavelengths. All right, so radio waves are over here longer, and as we move across, our wavelengths get shorter. So a microwave has a shorter wavelength than a radio, and an infrared is shorter than a microwave. Here is our visible light. So what we're going to do, I'm going to allow you to stop this video and move into the practice problems on the website.